Hi guys, I'm gonna go over the limit definition of a derivative, and this will just give you guys a little bit more insight about what a derivative is and how to figure out if a function is differentiable. Okay, so first let's just go over what does differentiable mean. So basically, if a function is differentiable, that means that the derivative exists at every single x value in the domain of the function. In order for a x value to be differentiable, at that x value, it must be smooth and continuous. So examples of spots that would not be smooth or continuous would be what's called a cusp or a corner, which occurs when you have, I like to call them little points. It's not smooth and you get what's called a cusp or a corner. All right, and then obviously if you have any jumps or removable discontinuities, that's not going to be continuous, therefore it's not going to be differentiable. Additionally, we have these vertical tangent lines, and these are not differentiable because at vertical tangent lines, the slope is d and e, therefore the derivative is also going to be d and e, and that should be pretty obvious, I hope. Alrighty, so let's get into the limit definition of a derivative. So basically, the derivative, the left and right hand limits of the derivative must be equal at that value that we are talking about. All right, and we'll get into that more later. All right, so first let's just be able to identify from a graph what x values would not be differentiable. Okay, so for starters, we have this x equals -5, and we have a vertical tangent line there. So at x equals -5, that function is going to be non-differentiable. Alrighty, and then moving to the next point, we have x equals 3, and we have a pretty strong corner there. And let me just kind of explain this a little bit more in detail. So we can see that the derivative here of the left hand derivative is going to be pretty low, let's just say like a 0.1. Here we have a negative, pretty high in magnitude slope, let's just say -2. So very clearly, those two are not equal, and we get this very sharp corner here. All right, so at x equals 3, that's going to be non-differentiable. Okay, and then moving on to this last one, we have a removable discontinuity, so that's going to be non-differentiable as well. Alrighty, so let's get into an example of figuring out if a function is continuous or differentiable, or both. Okay, so in this scenario, we are given a piecewise function. So for x values less than 2, we have the function 3x squared minus 5. And for x values greater than or equal to 2, we have x squared plus 3. Okay, so first let's just figure out if this function is continuous or not. So for a function to be continuous, our y value at that x value must exist. So there must be a point at that x value. Secondly, the limit must exist at that x value. And then lastly, the f of x value must be equal to the limit as x approaches that value of f of x, okay? So let's do that really quick. So first, let's just figure out what f of 2 is. In this case, we're going to be using the second function since x is equal to 2. And in this case, we get 7 because 2 squared plus 3 is 7. Okay, next we're going to do the limit as x approaches 2 of f of x. And since we have two quadratics here, the way that you find the limit is just by plugging in your x value. So in this case, if you plug in the x value to either of these, you get 7. Therefore, since the left-hand limits and the right-hand limits are both equal to 7, the overall limit is also equal to 7. So since our f of 2 and limit as x approaches 2 are equal, our function is continuous. Okay, so now let's move on to figuring out if the function is differentiable. Okay, so in order for the function to be differentiable, the left and right-hand limits of the derivative of the equation at that x value must be equal. Okay, so let's just find the derivative for x values less than 2. In order to do that, we're going to use what's called the power rule. If you guys don't know what the power rule is, feel free to go ahead and check out the power rule video that is in the tutoring modules. All right, but for now, I'm just going to move on. So the power rule, using the power rule to find the derivative values of x less than 2 is 6x. And using the power rule again for values greater than 2, using the second equation, you get 2x. Okay, so if we plug in our x value into 2 of those, and both of those, we get 12 for the left-hand limit and 4 for the right-hand limit. So we can see that those two limits are not equal. Therefore, the function at that x value is not differentiable. Okay, and just going over what this will look like on a graph, since we know the function is continuous, we know that there's no like poles or discontinuities. We just have two different limits of our derivative. So basically, we're going to have what is called a cusp or a corner, where we're having a sharp turn in the derivative, and that's going to form a point. All right. So you might be asked, what kind of non-differentiable function is this? And you would have to choose a cusp or a corner. Okay. So moving on. Lastly, I just want to go over how to match a graph of a function to a graph of a derivative. Okay, so for these, we're really just going to be looking at what is the slope doing. So is the slope positive? Is the slope negative? Is it a large positive value, low negative value, things like that. And then I also want to take into account horizontal tangent lines, because those are going to be your x-intercepts on your graph of the derivative. Okay, so just looking at number 1, we can see that we have a positive slope for this first portion of the graph. And then we have horizontal tangent line, which is going to cross the x-axis. Then we have a negative slope, another horizontal tangent line, then a positive slope. So basically, we want to look for a graph that has positive value, negative values, and then positive values with 2 x-intercepts. And the only graph that has any of those details is B. So with B, we have positive numbers, x-intercept, negative numbers, x-intercept, positive again. So the graph of the derivative for number 1 is B. Okay, so let's move on to number 2. With number 2, you can see that we have negative slope at the beginning for the first part of the graph, and then positive slope for the second half of the graph, with only 1 x-intercept. And the graph that matches that is A, because A only has 1 x-intercept, and it's specifically at the x equals 0, and we have negative for the first half, positive for the second half. Okay, so number 2 is going to be A. Okay, so number 3 is a little bit interesting. So with number 3, we actually do have this cusp or corner at x equals 0, right? So we can see that this makes a point here. So at x equals 0, that is going to be non-differentiable. So that's something you want to look for in the graph of the derivative. Okay, so secondly, we want to look for the slopes here, obviously. So here we have negative slope that increases in magnitude as we go towards the x equals 0 point, right? And then on the other side, it's kind of the opposite. So as we move away, we get less in magnitude, and as we become closer to the origin, we get larger in magnitude for positive values. And the graph that matches that is D, right? So here we have negative, and then it sharply increases in magnitude as you get to the origin. And then same over on the right side, we have larger magnitudes closer to the origin, and then it kind of decreases and decreases, okay? And we can see that we do have this vertical asymptote at x equals 0, which makes sense because, like I said, our derivative does not exist at x equals 0. Okay, so number 3 is going to be D. And then lastly, we know that 4 is going to be C, but let's go over why 4 is going to be C. Okay, so with looking at 4, it's pretty simple. We have a little bit of positive here, and then our slope is negative, and then our slope is positive again, and then negative. And then we additionally have 3 horizontal tangent lines. We have a maximum here, a minimum here, and a maximum here. So we want to be looking for a graph that has 3 x-intercepts, and 2 portions are going to be negative, 2 portions are going to be positive. Okay, so here we can see we have a positive, negative, positive, negative. the 4 portions, and we have 3 x-intercepts. So therefore, C checks out. C is the answer for that one. Alrighty, that's all I have on this today. If you guys need any other help in your calculus class, feel free to look at the other modules. Bye.